But we've had a friend of the conference step in at the last moment. Ruslan Salakhutdinov is the associate professor in machine learning at Carnegie Mellon University, and he will be joining us for a presentation via Skype. Can we please say hello to him?
Hello. So let me start sharing my screen. Excellent. So thank you very much for the invitation. Can you hear me? Excellent. Okay, great. So I know it's the last presentation in among the presentations, and I kind of decided to make the presentation be a little bit more technical. So I have to apologize beforehand. You're going to see some equations in this talk, but I think what I'd like to do is I'd like to talk to you about some of the recent advances that we see in the deep learning and machine learning community, particularly related to integrating domain knowledge into deep learning. So, throughout these presentations, I'm sure you've seen the impact of deep learning in speech recognition and vision, in recommender systems. Language understanding is a big area that I'm going to share with you. Drug discovery, medical image analysis. But if we step back a little bit, and if we look at statistical machine learning systems in general, and deep learning is an instance of statistical ML, we typically look for model architectures. We try to design better algorithms for learning. But how do we incorporate some prime knowledge or domain knowledge into these models? And that's what my talk is going to be about. And we can consider three classes of knowledge that we can incorporate. So, for example, we can try to incorporate relational knowledge. We can try to incorporate logical rules or scientific knowledge. For example, if we look at relational knowledge, things like Bob is the father of Alice, right? How can we incorporate that structure? Well, those type of knowledge is available to us from either relational databases or knowledge graphs. And there has been a lot of work in our community on trying to solve these problems. You've probably heard about probabilistic graphical models. There are certain things that can model relational dependency networks and so forth. More recently, we start seeing things like embeddings. This is the way of trying to represent, for example, words or images in vector space and doing some manipulation in vector spaces. And I'm going to show you some examples of that. In particular, I'm going to show you how can we incorporate these knowledge graphs into deep learning systems for question answering. So we'll see some examples of that. There's also, a lot of first-order logical rules knowledge that we can find online, or could be part of some relational knowledge that we have. So, for example, maybe we can incorporate if an object has a wing and a beak, that it's a bird, right? Particularly, these types of systems would be quite useful for improving our image recognition systems. We can try to, again, encode these logical rules using graphical models. There's tons of work on using, horn clauses, probabilistic context-free grammars, and so forth, right? And what I'm going to show you is I'm going to show you one way of trying to incorporate those knowledge bases into deep learning via so-called distillation framework. And I'll briefly mention what that is through this talk. And there is a lot of work also trying to look at, maybe physics, and incorporate physical laws into our prediction models and deep learning models, Newton laws of motion. Can we incorporate conservation laws and principles and invariances? It's a big area of research, and we're not very good at doing it right now, especially with deep learning approaches, right? So, for example, we can learn partial differential equations and dynamical systems and so forth, right? So in this talk, I'm going to primarily focus on the first two ways of incorporating the knowledge. Let me show you one example where it comes in and where it's important. There's been a lot of work on so-called reading comprehension tasks. So imagine that I give you a paragraph, such as what you're seeing here. It talks about gravity and the meaning of it and so forth. And then I give you a question: what causes precipitation to fall, right? And the answer here would be gravity. Right? But there is a lot more that's happening in the paragraph. So if I ask you this question in natural language, finding the answer is actually pretty difficult. And you can imagine that building systems that look at technical manuals or technical documents, or, there's some work that people trying to construct, ask questions about tax laws in a particular country, right? And build these automated systems that can answer those questions. And there's been a lot of success in kind of, learning from these unstructured text. I just give you some Wikipedia article and ask you a question about it. A lot of these systems rely on so-called recurrent networks, one way or another. And these recurrent networks, basically what they do is they have some hidden representation at the previous time step. You have some representation at the current time step, and then you combine them, and it goes through nonlinearity to generate the next time step, right? The hidden state at the next time step. So you can imagine that x1, x2, x3 are words in a sentence, and you kind of go and you update your hidden state as you're reading a particular sentence or as you're reading a particular paragraph. And if you look at these systems that are successful today, these are fairly complex systems. What you're seeing here is you're seeing, what's called a bidirectional type of network that looks at words, sentences, combines them. So there's something that's called gated attention mechanisms that looks at the query or question that you're asking, understands what's going on in the text, makes multiple passes, and then predicts the probability of the correct answer, right? And, there's tons of versions of these types of networks, and they've been quite successful, in the last couple of years. In fact, it's been so remarkably successful, it's surprising sometimes to see that, you ask a general question, and these models plowing through unstructured text like Wikipedia articles and coming up with correct answers, right? But one of the big questions that we have so far is that, well, we have some text, but how can we incorporate some prior knowledge, right? There's something about word relations. There is something that's called coreference dependency pairs that can help us understand better the language, and how do we incorporate that? So let me show you one way of incorporating relational data. So imagine that I'm trying to build the following system, and you can imagine, these kinds of systems have a lot of practical applications. So, for example, I can ask my system who voiced Meg in Family Guy, and there are two answers: Lacey Chabot and Mila Kunis, because they both voiced Meg in Family Guy. So, Family Guy is a show; it's a cartoon show. Or I may ask who first voiced Meg in Family Guy, right? And I want to be able to answer that correctly. So how do we do it today? In a lot of industrial systems, if you actually have, if you're using any of the personal assistants today, basically they rely on knowledge graphs. Knowledge bases is knowledge source, right? So you build this huge graph, and the idea is that if I ask you this particular question, who first voiced Meg in Family Guy, then there's something that's called semantic parsing, which basically identifies that Family Guy is a show, maps it into the right part of the knowledge graph. It identifies that Meg is a character in that show, maps it to the right part of the knowledge graph, and then you kind of looking through these links, you can answer the questions like who voiced or who played and who's the director and so forth. The issue with a lot of these systems today is that these knowledge graphs are typically incomplete, they're noisy, but more problematic is trying to map a question in natural language to one of these blocks. So, if you're using personal assistant, sometimes if you ask a question and your personal assistant completely gives you the wrong answer, most of the time it's because this semantic parsing is failing. So it just doesn't understand, what the questions are and how do you map into the knowledge graph, right? And then more recently, in just the last few years, people started saying, well, actually, maybe we can build these deep learning models using recurrent networks, which is what's called reading comprehension task, that actually looks at the raw data like Wikipedia and then comes up with the answer. And these models, become more and more dominant, and they actually, so far competing quite well with these knowledge graphs. But you can answer any question on the web in principle, right? But at the same time, these models sometimes can fail, right? Sometimes if you're trying to answer a particular factual question, they can fail. But what you can do, and this is one way of doing it, is you can construct the text augmented knowledge graphs. So here you basically have sentences or Wikipedia articles that talk about Meg Griffin, Family Guy. You have your knowledge graph, and you can use machine learning type of algorithms, particularly use what's called graph convolutions to do propagation on the knowledge graph, and you can use recurrent networks to do propagation in unstructured text. And you can kind of share information between these two different sources of data. And there is, here's just a more mathematical tools of how you do this. Entities in the knowledge graphs can influence representations that you're getting from, trying to read articles from Wikipedia. At the same time, whatever you're reading on the Wikipedia can actually influence your knowledge graphs, and potentially you can build better knowledge graphs. And so these kinds of, there's a number of approaches that exist today that kind of try to combine and build these hybrid approaches. And I strongly believe that in the future, you'll start seeing better and better personal assistants, systems that can answer complex questions in this type of a regime, right, where you're combining prior knowledge with the knowledge graphs with, unstructured knowledge that you can just mine from the web. Right. Let me show you another way of incorporating prior knowledge. These incorporating logical constraints. So imagine that, you have some model, so here I'm denoting it by P of theta. This could be some statistical model, could be deep learning model that's trying to predict a particular label or classify images. And let's say I have some kind of a function, what's called constraint function. And this constraint function is basically says, well, this function takes high value if X is better with respect to a particular knowledge. So if X satisfies the knowledge constraint, then this F will have high value. Let me show you an example. Here's a classical example in trying to do what's called pose-conditioned human image generation. So I give you an image, and I give you the target pose. And what I want to build is I want to build the same image or the same person, but under a different pose, right? That's a quite challenging task because, this is the first time I'm seeing this person. I want to be able to generate this person in different views, for example. And this could be applied for other objects, for example. But there's a data set that kind of constructs and gives you that, and there's a true target. But what you can do is maybe you can incorporate some what's called structural consistency, and you can learn what that means. For example, one way of doing it, you can say, well, if I can, parse this particular image, and this is the head, and this is the arm, and I want to make sure that my generated arm is consistent with the true target's arm, then that's good. If it's not consistent, then it's not good, right? So imagine that you can build these constraints into your model, and this is particularly becomes important in the areas where you have some prior knowledge about these constraints, right? In medical domain or in, when you're trying to make a prediction. Here's another example. There is a lot of work on sentiment prediction tasks, classifying reviews as positive or negative. It's just a classical example. And let's say I give you this particular sentence. This was a terrific movie, but the director could have done better, right? If you look at this sentiment, you actually say, well, it's a negative sentiment, right? Even though it contains words like terrific and better, right? So if I just use naive approach, I would probably say, well, somebody says it's a terrific movie. That's a positive sentiment. However, there are these logical rules that basically tell you if you have a sentence with a structure A but B, then the sentiment of B dominates. Every time, you say something like, this is great, I love it, but it immediately implies that, the sentiment is probably not going to be as good, right? And that's a logical rule. And the question is, how do you incorporate that structure when you're learning your models? And so one way of incorporating that is to try to maximize this quantity. And it's an expectation. And intuitively, what that means is basically, it sort of says, put your predictions, your model that you're building, in the space that's consistent with your rules or consistent with your constraints. Don't put your predictions anywhere. Just constrain them to be predictions that are consistent with your rules or consistent with your logical rules, right? It's a very natural way and mathematical way of incorporating that. And then you can optimize the objective. There is kind of like regular objective. Let's say you're trying to improve sentiment classification, for example. But this term is actually trying to say, be consistent with my rules. And it turns out that it's actually difficult to optimize. And there is a beautiful framework. It's called posterior regularization. What it does is it basically says, instead of trying to solve the original problem, I'm going to try to solve a slightly different problem. And this different problem has this particular formulation, right? So there are lots of equations here. But what this formulation is essentially doing is it's essentially saying, if I have my prediction, which is P, right? Let's say I'm predicting positive sentiment. And this is my rule or my constraint, I'll say my logical rule. If my logical rule, the output of my logical rule says, yes, it's a positive sentiment, and my prediction says, well, the probability of positive sentiment is 0.8, then because this is consistent with my rule, I'm actually going to increase this probability. So this 0.8 is going to turn into 0.9, for example, because it's consistent with my rules. If, however, it's not consistent with my rule, then this F will be small or it's going to be negative. And if it's small and negative, it will reduce this probability down, right? So whatever I'm making prediction that's not consistent with my prior knowledge, that probability is going to go down, right? Even though my model, original model might say, yes, it's highly probable, but these rules kind of overwriting my predictions. And, you know, one example of trying to incorporate logical rules into your predictions, particularly deep learning models, imagine that you have some P of y given x, your deep neural network, you know, you're trying to classify sentiment, you're trying to classify images, and you have some kind of rules. And then the rules are basically telling you, you know, is it consistent with your logical rules? And you have to come up with those rules yourself. And within this posterior regularization framework, what you're essentially doing is you're essentially saying, I'm going to adjust my predictions in favor of logical rules. So if this particular prediction satisfies a whole bunch of logical rules, then I'm going to increase its probability. If it doesn't, I'm going to decrease the probability, right? And so how do we train these types of models? And there's a beautiful framework of something called knowledge distillation. And knowledge distillation is really what it's trying to do is it's trying to say, well, let's say I have, it's typically is done in the context of what's called ensemble networks. So typically, let's say I have multiple predictions. I have multiple neural networks that's trying to make a prediction, and I want to have like a single model that predicts just as good as the ensemble of these models. And what I'm going to do is I'm going to try to match the soft predictions produced by all of these networks with the predictions produced by the teaching network, right? And so mathematically, imagine you have some network that's making a prediction. The way that you're optimizing these models is you say, well, this is a true label. This is trying a sentiment of the sentence or the class of a particular image. And this is what my neural network is predicting. And this is what everybody is solving when they're building these deep learning models. But what I'm going to do is I'm going to have an additional term. And the additional term here is the soft prediction. It's the prediction of this modified network. This is prediction of the network that incorporates logical rules and constraints. And what I'm going to do is I'm going to say, make sure that whatever this network is predicting is consistent with what my neural network is predicting, right? So it's almost like two objectives. One objective is trying to get as good classification as possible, as bad prediction as possible. The other one is trying to say, no, stay close so that my predictions are consistent with the rules. Right, and so intuitively, and there's a balancing factor that balances between the two. So intuitively, you know, pictorially, what happens is that you have some labeled data, you're training your model, and then you have some logical rules. Right? Think of it as a constraint set. And what I want to do is I want to project what my prediction is onto this set. So my prediction is consistent with the logical rules, right? And so this is exactly what's happening by, you know, having this teacher-student network. So the teacher is really incorporating logical rule. The student is really trying to get as good accuracy as possible. And then there's a projection operation that's trying to match the two. Right? You can also use unlabeled data potentially for improving these systems. So this is just one example of what you can do. And again, this is a pretty hard example because you need to be able to generate, given the source image and the target pose, you want to generate this person in this new source. And these are actually generated images, which is fairly impressive. And the constraints you use are the constraints on the body parts. You want to make sure that the arms are consistent, the head is consistent, and so forth. And that improves quite substantially the prediction accuracy of these models. Here's just, quickly to show you another example, which is pretty hard to satisfy, which is I give you the template and I want to generate the text consistent with this particular template. And in general, it's fairly hard to do so, right? So for example, if I say, generate me a sentence consistent with meant to, not to. The true target was meant to dazzle, not to make sense, and the generate was meant to dazzle, not to make it, right? For example. And so you can try to learn these constraints and say, I want to generate something that's consistent with those constraints. And so you can generate, in principle, you can generate reports, or you can generate paragraphs where you give it some constraints and say, be consistent with this template, whatever it is that you're generating. And you can learn what that should be. And so, one of the forms, and the reason why I've decided to talk about this particular effort is in our community, as you know, in deep learning, there's a lot of successes in images, speech, and so forth. But the issue with a lot of deep learning models today is that they require a lot of labeled data, a lot of training data. And in many cases, a lot of researchers or even people working in particular domains, such as medical domain, for example, but also in natural language processing domain, you have some prior knowledge, you have some rules, or you have some knowledge graphs that you want to incorporate into your models, right? And so far we've only considered simple forms of knowledge, but obviously, there is, if we want to incorporate human knowledge is abstract. It's built on high-level concepts, right? So for example, if I want to recognize or generate an image of a dog, I want to say, well, this particular image has 4 legs, so that's why I think it's a dog. It's not something else. Or, perhaps if I'm trying to make a prediction for this image and the prediction is elephant shoe, the reason why I'm making this prediction is I can see there's a trunk and it looks like a mouse and there's a tail. And these 3 things actually tell me that this is elephant shoe, right? A specific type of a little mouse. And so how do we incorporate this knowledge and how do we efficiently integrate this into deep learning models? It still remains a big challenge. But in our community, just in the last year or so, we're beginning to see how we can, how do we even incorporate these abstract, common sense knowledge into these deep learning models. And I've shown you just a couple of ways of doing it, but these are still baby steps towards, towards making our systems basically be much more intelligent rather than just, doing a standard pattern recognition, which is what a lot of deep learning models actually do today. So on that note, thank you very much.
So I don't know where to look for the questions. Are you still here?
Yes.
Wonderful. All right, perfect. So I will talk out into the ether. This was a very great presentation. One of the questions I have is, because it seems like what you're doing is you are pairing, knowledge-based models with knowledge-free prediction and seeing if something better comes out the other end. If I'm basically reading that right, then is this something that could help us predict chaotic systems like the weather, where we can't really see but beyond a couple of Lyapunov times, but maybe if we have the rules of physics implemented in this model, we could think about looking further.
Absolutely. I think that's a great point making. I think that, there is a wonderful program that's, being sponsored by DARPA called Physics of AI, which is essentially trying to do exactly what you're saying, right? In many cases, trying to predict the weather patterns is extremely difficult. These are chaotic systems. But at the same time, there are underlying physical laws how these systems can evolve, right? So just using deep learning blindly, saying, here's the input, this is what I'm trying to predict, which would be inconsistent with the laws of physics, doesn't make much sense. The question is, how can you incorporate this into your predictions and then move beyond? Because, if we just have the laws of physics, or if we just have, logical rules, in some cases, we also want to extract, we also want to be able to drive predictions using data and using past data as well. So just like you're saying, these are the hybrid models. And what we've been doing actually in the last, year or so is we're basically trying to also say, well, we also want to be able to learn the confidence of these logical rules, because sometimes when we come up with these rules, they might be wrong. Maybe sometimes these Lyapunov type of functions or the physical things that we believe are right, maybe some of them are not quite right. And so, if you have enough data, maybe data can override some of these rules. But at the same time, in many cases, if, like in computer vision, a lot of us are trying to solve one-shot learning task, which is, I show you a new class or a new concept, and I want to be able to learn it from a few examples. And if I know something about animals, right, I can quickly try to, come up with some of these logical rules and my prior knowledge of what the world should look like. And I can, and I should be able to learn, very quickly what that concept is, right? So how do we?
I think we lost this. We lost the sound, unfortunately, but that was a pretty good answer before you died. So thank you so much for your presentation. Can we please give him a big hand?